Safety Toolbox Talk number 268. Essential Safety Protocols for Reactor Operations. Reactor safety in the chemical industry is crucial due to the inherent risks involved with handling hazardous materials, chemical reactions, and high-pressure and high-temperature processes. Below are some special safety considerations for reactors used in the chemical industry. 1. Chemical reaction hazard control. Reaction monitoring. Chemical reactions can sometimes be unpredictable. Continuous monitoring of the reaction parameters such as temperature, pressure, and chemical composition is vital to prevent runaway reactions, which could result in explosions or toxic releases. Heat control. Exothermic, heat-producing reactions need to be properly controlled to avoid temperature spikes that can damage the reactor or cause uncontrollable reactions. Cooling systems must be reliable and responsive. 2. Explosion and fire prevention. Use of inert gases. For processes involving flammable chemicals, inert gases, like nitrogen, can be used to blanket the reactor to prevent ignition. This is crucial when working with solvents or gases that can form explosive mixtures with air. Flame arresters. In systems where combustion risks exist, flame arresters should be installed in vent systems to prevent fires or explosions from propagating through pipes. Explosion-proof equipment. Equipment should be designed to withstand explosions or be placed in explosion-proof enclosures to protect workers and prevent escalation in case of accidents. 3. Pressure management. Pressure relief systems. Reactors should have pressure relief valves, rupture discs, or safety relief systems to release excess pressure safely and avoid structural damage or explosion. Venting systems. Properly designed venting systems are essential to safely direct gases away from personnel and the environment during pressure relief or emergency situations. 4. Corrosion and material compatibility. Material selection. The materials used in the reactor, e.g., glass-lined, stainless steel, Hastelloy, must be compatible with the chemicals being processed to prevent corrosion or contamination. Improper materials can lead to equipment failure and hazardous leaks. Corrosion monitoring. Regular checks for signs of corrosion or wear are critical, especially in reactors that handle corrosive chemicals. Specialized coatings or linings should be used when necessary. 5. Runaway reaction prevention. Reactor control systems. Automated control systems should be installed to quickly respond to changes in reaction conditions, e.g. pressure or temperature increases. Alarms should be in place to alert operators of abnormal conditions, and safety interlocks can shut down processes automatically if limits are exceeded. Reactant addition control. Reactants should be added in a controlled manner to avoid sudden surges in reaction rates. In many cases, continuous or gradual addition of reactants is preferable to batch addition. 6. Toxic gas and liquid containment. Gas scrubbers and absorbers. Systems should be in place to neutralize or capture toxic gases before they are released into the atmosphere. Scrubbers and filters should be used to ensure gases such as chlorine, ammonia, or hydrogen sulfide do not pose environmental or health hazards. Secondary containment. In case of spills or leaks, secondary containment systems such as bunds or dikes should be installed around reactors to prevent chemicals from spreading. 7. Emergency cooling systems. Emergency cooling mechanisms. Reactors processing heat-sensitive or exothermic reactions should have backup cooling systems, such as emergency cooling water or quenching systems, in case the primary system fails. This is essential for preventing runaway reactions. Thermal cutoffs. Installing thermal cutoff devices that automatically stop the reaction or cool the reactor when critical temperatures are reached. Preventing contamination. Clean-in-place (CIP) systems. Reactors should have systems for cleaning without opening the reactor, clean-in-place, especially when dealing with sensitive or hazardous chemicals to prevent contamination and reduce worker exposure. Avoiding cross-contamination. If the same reactor is used for different chemical processes, stringent cleaning and validation procedures should be in place to avoid cross-contamination between batches. 9. Handling dangerous byproducts. Safe byproduct disposal. Some reactions may produce dangerous byproducts like acids or toxic gases. These byproducts need to be carefully neutralized, treated, or stored in designated areas until proper disposal. Reactor integrity monitoring. Non-destructive testing. NDT regular inspections using non-destructive testing methods, like ultrasound or radiography, can identify internal defects, cracks, or weaknesses in reactor walls before they become critical. Vibration monitoring. High-pressure reactions can cause vibrations, which could indicate mechanical or chemical issues. Continuous vibration monitoring helps in early detection of potential problems. 11. Environmental protection measures. Effluent treatment. Reactors in the chemical industry often produce harmful effluents, liquid or gaseous. Treatment systems should be in place to neutralize or process waste before discharge into the environment. Air quality control. Use appropriate filtration, scrubbers, and ventilation systems to minimize the release of toxic or harmful gases into the atmosphere. Human factors and safety training. Operator training. Personnel must be well trained in chemical safety procedures, emergency response, and the correct operation of reactor systems. They should be aware of specific hazards associated with each chemical process. Human-machine interface (HMI) control systems should be designed with a user-friendly interface to minimize human error. Clear display of critical process variables, easy access to emergency shutdown controls, and audible/visual alarms help ensure safe operation. 13. Safety instrumented systems, SIS layers of protection analysis. LOPA studies help identify additional protective layers needed to mitigate risks associated with chemical processes. Redundant safety systems, backup systems such as double-checking instruments, redundant alarms, and dual control loops provide additional layers of safety in critical operations. 14. Fail-safe systems, automatic shutdown mechanisms. In case of system failure, reactors should be equipped with fail-safe mechanisms that automatically halt operations and trigger cooling or depressurization processes to prevent accidents. By implementing these safety considerations, chemical reactors can be operated safely, reducing the risks of accidents, protecting human health, and ensuring environmental safety. Thank you.